All right, so welcome to video 15.1. We're going to focus today on what's called simple harmonic motion. All right, so simple harmonic motion is a type of motion in which an object is moving back and forth and kind of repeats the same motion over and over again. So you kind of imagine a thing going back and forth, back and forth, back and forth. But it's a little bit more particular than that because sort of how the velocity changes as it goes back and forth is important. All right. And in order for your velocity to change as it goes back and forth, you have to have a force producing that change in velocity. All right. And what characterizes what is called simple harmonic motion is this: the force that causes it to be constantly changing directions, to oscillate back and forth. Simple harmonic motion is motion in which that force that causes that is proportional to the displacement from the center of the oscillation. So if this is the center of oscillation and my object's going back and forth, back and forth, back and forth, in order to be simple harmonic motion, the force pulling it back towards that origin has to be proportional to the distance away from the origin. In English, F equals negative kx, just like we learned for a spring, right? We did these spring problems, right? Where the amount that you squish or stretch your spring determines how much force it exerts, kind of returning it back to that unstretched position. All right, so we got to do real quick a couple of definitions, and these are review. So hopefully remember period, capital letter T for period. Oops. Period is the amount of time that it takes for your object to complete one full cycle. So 1 Mississippi, 2 Mississippi. So that would have a period of 2 seconds, right? Your frequency is the number of cycles you complete per second. So kind of continuing with that. So a minute ago, we just had 1 Mississippi, 2 Mississippi. So if the period is 2 seconds, then your frequency is the number of cycles you complete per second. So if it takes 2 seconds for one cycle, that means in 1 second, you'll get half of a cycle. So your frequency would be half of a cycle per second, which we write as 0.5 hertz. Okay, remember, hertz is just cycles or whatever per second. All right. So the next thing we need to deal with is angular frequency. I'm going to come back to that in a minute. All right. So I guess the first thing I'm going to do is let's observe an example of simple harmonic motion. So to do that, I'm going to go over here and then I'm going to click this button and here we go. All right. So what I've got here is, oops. Oh, good. It did do what I wanted it to. All right. So what I've got here is I've got this, this block. All right. And you can see it's attached to the spring. Notice this right here is our position of 0. So when the object is over here, we're at what we're going to call X max, the maximum position, right? And because the spring is stretched to the right, the spring wants to pull it back this way, right? And so what's going to happen is it's going to speed up as it gets closer to the origin, right? As we unstretch the spring, the box is going to speed up until the spring gets to that unstretched position. But at that point, we're going to velocity this way. So it's going to want to keep moving that way. And as it does that, it's going to compress the spring. And as it compresses the spring pushes back the other way and slows it down where it stops over here. Okay. So let's observe that, shall we? Boom. All right. So as this happens, well, we'll come back to the graphs in a second. All right, so let's do it. Let's go ahead and do it. All right, so notice we're at our maximum position. Velocity right now is 0. When I click run, watch what happens. Oops, absolutely nothing is what happens. Let's try that again. There we go. Speeds up, slows down, stops. Speeds up, slows down, stops. Speeds up, slows down, stops. So it stops at the endpoints, and then it speeds up and slows down. Speeds up and slows down. Okay, so let's take a look at the graphs. I'm going to hit reset and let's do this again. So this top graph over here is our position time graph. All right, notice right now we're at our maximum position, right, at a velocity of 0. So our graph is going to start out horizontal. and then it's going to start moving in a negative direction faster and faster and faster. So what's going to happen is the velocity graph, let's see, from here, orientation. Sorry, I'm getting a little dyslexic here. So the graph is going to start out like this, and then it's going to get steeper, 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 steeper as it speeds up. Then it's going to slow down and get less steep, less steep, less steep, right? Then it goes the other direction. So let's watch. What I want you to focus on right now is just this position time graph. All right, here we go. Speeds up, slows down, speeds up, slows down, speeds up, slows down, etc. Okay. So notice if we kind of think about our slopes, so slope is zero, slope is zero. So these all represent the points where it stops. These points in the middle, notice that's where the graph is the steepest, because that's when you're at your origin. It's the point where the spring has stopped causing it to speed up and it's about to start causing it to slow down. Okay. So these first three graphs are important. It turns out that position, velocity, and acceleration are all sine or cosine graphs. And then we'll learn about the potential energy and kinetic energy graphs. Those turn out to be sine squared and cosine squared graphs. And we can learn why that is as we go through the video. All right. So when you have simple harmonic motion, the position, velocity, and acceleration can all be expressed in terms of a sine or a cosine graph. And then we'll talk more about the potential energy later on. All right. So with that in mind, let's take a look at an example, I guess. All right, so I want to exit out of this dude and I want to go over here. All right, so let's start by looking at this graph. I'm kind of going out of order a little bit. So here we've got a position time graph, right? And what you can see by looking at this thing is it looks like our maximum position is 5 and our minimum position is -5, right? And hopefully from your math class, you remember that the period of a sine or a cosine wave is, just like in physics, the time to complete one motion. So my period in this example is, right? So my period here is 8 seconds. I guess if you want to make a note of it, your frequency is going to be 1/8, which is 0.125 hertz, right? But the problem is this, we want to write this as a sine or a cosine function, right? And so it looks like this is a sine function, right? Because the sine of 0 would give me 0. But the problem is the sine of 8 is not 0. Okay, so what we need to do is we need to sort of create a conversion factor so sine and cosine repeat every time you go through 2 pi radians, right? Every time you go around a circle, you go 2 pi radians. That's when your sine and cosine functions repeat. So what we need to do is we need to sort of convert this 8 into 2 pi. Okay, so we're going to imagine, we need to sort of convert the 8 into 2 pi. All right, so in order to do that, what we're going to do is we use what's called angular frequency. All right, and what we're going to do is we're going to kind of take that period of 8 seconds and divide it up into 2 pi chunks. Okay, and so then your angular frequency is how many of those 2 pi radians you go through each second to get to 8 seconds, right? So your angular frequency is, oh, it's right here. I don't know why I'm rewriting it. Let's do this. Boop. And then we'll scroll down. Whoa, try that again, scroll down. So here's the equation for angular frequency. This is the one that's the most intuitive to me. We're taking 2 pi radians and splitting it up into, in this case, 8 seconds worth of time. Okay. So we're taking our period, 2 pi, and splitting it up into 8 seconds. And that'll tell me sort of the number of radians that the object completes per second. All right. So the symbol we use for angular frequency, I think I already kind of alluded to that, is the Greek letter omega. This is similar to, but is not the same thing as angular velocity, which is frustrating because in previous chapters, we used omega to represent angular velocity. Now it's representing angular frequency. So you need to remember, if you're doing simple harmonic motion, omega is angular frequency, not angular velocity. Okay. So once we figure out what omega is, we can take any position time graph or velocity time graph or whatever you'll see, and write them in terms of a sine or a cosine function, okay? So to do that, it's gonna look like this. So your position in simple harmonic motion is going to either look like this, x max times the cosine of omega t, or x max times the sine of omega t, all right? If it happens that it's sort of neither a sine nor a cosine function exactly, you know what I mean? Like if it's shifted so that it doesn't start at either a max or at zero, then you can use a phase change and that'll satisfy anything. But for the scope of our class, we're gonna not worry about this phase change. But if you're somebody who's wondering like, well, sine and cosine doesn't cover everything, but the idea is if this allows you to kind of shift the function left or right, you know, so that you get the sort of the right origin on your graph. Cool. If that made sense, cool. If not, don't stress about it. It's not a big deal. I'm happy to talk to you about it in class. All right. That's not on the, you know, not a thing we need to know anyway, but I just felt like I should include it. Okay. So the idea is both of these functions here, remember sine, well, both sine and cosine oscillate between +1 and -1, right? So at its biggest, sine and cosine are 1. At the smallest, sine and cosine are -1, which means this value is going to oscillate between positive xm and negative xm. All right. So xm, again, refers to the maximum displacement. We often just call it amplitude. All right. The amplitude is just your maximum displacement from your origin. All right. This omega t, the textbook name for it is phase of motion. Don't know that you need to worry about that, but I figured I'd put it in there again. All right. So I think this is probably easiest to see by just doing an example. And I guess maybe before we do, I should probably take a quick second and just do a super quick review of what sine and cosine functions look like. So here's, oh, which order do I have it up here? We got it cosine first. All right, so let's do that. So here's cosine of x. Here is x. So cosine of 0 is 1, and then it oscillates like that, so that our minimum is -1, and then this is 2 pi, which means this would be pi, this would be pi over 2, and this would be 3 pi over 2. Okay, so that's what the cosine graph looks like. And then the sine graph, whoops, looks like this. Set up the same scale. Sine starts at 0. I don't know why I decided to change colors. It also oscillates between 1 and -1. And so it's going to go whoop, whoop. So long story short, basically what you need to know for the purposes of us or of this class is that the sine of 0 is 0. So if the graph starts at the origin, it's going to be a sine curve. If it starts at the maximum, it's going to be a cosine. If you have a graph that is one of them inverted, then you just stick a negative sign in front of it, right? Cool. And then if it's not one of these 4 shapes, then that's when you have to use this phase change, but we don't need to worry about that this year. Okay. So let's do an example. All right. So this guy, whoops. You guys can see this menu that I keep moving here. But okay. So, oh, it starts at 0. It's going to be a sine curve. Cool. So here, oh, so this is a position time graph. So position at time t is what? Well, we know it's a sine function. So let's go ahead and write sine. Now, ordinarily, sine oscillates between 1 and -1. Oh, this goes between 5 and -5. So this is going to be 5 times the sine. It's +5 because it goes up first. If it had gone like this, then it would be -5. So now the last thing we got to do is we got to figure out what this whole omega t business is. All right, so here's the trick with that. What we want to do is we want to take our period. So if you look at this graph, you can see that the period is 8 seconds. And what we want to do is smush that 8 seconds into 2 pi radians. Okay, so remember, your angular frequency is the number of radians you have to get per second. So the idea is I need 2 pi radians in 8 seconds, which is the same as pi over 4. So that is my angular frequency. So my actual function is going to be position at time t, which is 5 times the sine of pi over 4 times t. And notice, so here's where this will sort of all come together. Hopefully this will help you make some sense of the angular frequency thing. Check it out. If I put 8 back into this equation, then pi over 4 times 8 is 2 pi. Oh, and the sine of 2 pi is 0 again, and that gets me back through my full cycle. Okay? So that is how you can take a position time graph and write an equation for the function. All right? So what are some different things you could have? So here we've got 2 different graphs. There's a pink graph and a red graph. Let me maybe embiggen those so you can see them a little bit better. Whoop. All right, so here the pink and red graph are the same, right? They have the same period. The only difference is they have different amplitudes, right? The pink one has an amplitude of x prime m, whereas the blue one has an amplitude of just xm, okay? There, the prime is just notation. It doesn't mean derivative, all right? So it's just 2 different xm's, okay? All right. All right, over here, the red or pink and blue graphs are the same, except for the period, right? They both have the same maximum amplitude, but it looks like the period of the blue one is this, right? Because that's the time it takes to complete 1 cycle, whereas the red one is completing that 1 cycle in half of the time, right? So it looks like that's t over 2, okay? Cool, cool, cool. So what does all of this get us? So suppose I gave you some, simple harmonic motion, and we already had our expression for the position at time t. All right. Well, what we can do is use everything we learned in, I don't know, I guess unit 2 it would have been. And we can use the position to find the velocity, use the velocity to find the acceleration, right? We're going to take derivatives. All right, so let's do, I want this to be a different color so it stays out. So let's find out what's the derivative of x with respect to time. Oh, I took physics. That's velocity at time t. Well, how do you take the derivative? Let's see. So the derivative of cosine looks like this. So my slope is going to be negative. So that's going to be negative sine of omega t. But then we got to do the chain rule. We got to take the derivative of this also. So the derivative of omega t is omega. Oh, and then I got to bring down my constant xm. Okay, so that's my velocity at time t. All right, let's take another derivative. Do this one in, how about a lovely, let's use orange. All right, so now I'm going to take the derivative of v with respect to time. Oh, that gives me acceleration at time t. So the derivative of sine is just cosine of omega t. Oh, shoot, but I got to do the chain rule. I got to take the derivative of cosine. I'm sorry, I got to take the derivative of omega t. That's going to be omega. So I got to bring down this omega times this omega, right? For my chain rule, I'm going to get omega squared and negative xm. Okay, so let's clean that up so it's not all scribbly. Oh, cool, now I found the acceleration. All right, well, if it's accelerating, there must be a force. So net force is, mass times acceleration. So if I know the mass of the oscillating thing, I can find my net force. So that's going to be negative m. Oh, shoot, I don't like how I did this. I'm going to do a thing real quick. I apologize. know this is frustrating when you're trying to take notes. I'm going to just flip-flop these. I want omega and then xm. I'm going to write this as omega times xm. Same thing down here. I'm going to write that one as omega squared times xm, and you'll see why I did that in just a second. It doesn't really matter, but okay. So back to where I was. So I'm multiplying now by mass to get my force. So I'm just taking, this is my acceleration, multiply it by mass, that'll get me net force. So that gives you mass, times acceleration, which is omega squared xm cosine of omega t. Oh, cool, there's my net force. Cool. So, worth noting, in my original function, my maximum position is xm because I'm multiplying cosine by xm. So what would my maximum velocity be? What would my maximum velocity be? Well, sine oscillates between 1 and -1. So it looks like my maximum velocity is omega squared xm. So V max is omega times xm. I think I mistakenly said omega squared just now. Similarly, my maximum acceleration, well, cosine oscillates between 1 and -1 times omega squared xm. So my maximum acceleration is omega squared xm. All right. And my maximum force, again, same logic, is going to be m times omega squared xm. Cool. All right. And then finally, if we scroll down a little bit here. Oh, shoot. You know what? I'm going to do this again. I'm going to rewrite a thing. So what we figured out here, do I want to do this? All right. So write that down if you haven't, because that's about to go away. All right. Cool. Oh, shoot. Oops. Okay, so take a look at these two functions. I'll highlight them. So that's my position at time t. This is my restoring force at time t. Oh, well, this is x of t. Oh, huh. So what we just learned here is, and this is super important, we just learned that my restoring force at time t is equal to my position at time t times negative m omega squared. Now remember, the definition of simple harmonic motion is motion in which the force is proportional to the displacement. The force is equal to negative k times x. I'm mad that I wrote that like that because it looks like a fraction now, and that wasn't my intent. So force k times x. We just found our spring constant. We just found our spring constant. We found our constant of oscillation. There's a name for it that I'm drawing a blank on right now. We'll get it in class if I don't come up with it here by the end of the video. Oh, cool. So we just learned that our constant k is m omega squared. Hooray! That's super cool. I will tell you, kind of like the gravitation chapter where I commented, if you forget the equations, you can derive them. I do that in this chapter all the time because I always forget what k is, but it's super easy to run through this calculus and figure it out. I shouldn't say super easy, but it's a thing you can all do. And the more you do it, the easier it'll get. All right. Okay, cool. So we've now covered everything up through here. So how do we get the period? Oh, well, let's see. Up here, we discovered that K is m times omega squared. But remember, omega is 2 pi over t, right? So I think if I plug this into here, I ought to be able to come up with an equation for the period. Let's do it. I'm super excited. I can tell that you are as well. All right, so, stupid smartboard. All right, so here we go. So K is m omega squared. So that's m times 2 pi over t squared. Let's solve for t. So here we go. So K is m times 4 pi squared over t squared. Let's multiply by t and divide by k. Multiply by t squared rather. So we get t squared equals m times 4 pi squared over k, and then square root both sides. And you get period equals, well, the square root of this is just 2 pi again, times the square root of m over k. That right there, everything we just ran through here is this section, okay? In a minute, we're gonna get into energy, but at that point, it's just 1/2 mv squared and 1/2 kx squared, okay? Right, 1/2 mv squared is a kinetic energy. So I guess let's just make a note of that. I don't know why I'm writing this down right now. Oh, cool, now we can find our kinetic energy and we can find our elastic potential energy, often just called U. That's 1/2 kx squared. And oh, look, we already know what k is, right? Remember, k was m omega squared. All right, so now it's just a matter of parsing through all this and being able to put it all together. All right, so let's do it. Oh, well, that's what the next screen was. All right, so notice our system can be thought of as an oscillation between potential and kinetic energy. Here's our potential energy. Here's our kinetic energy. Our total energy. So remember, at the end points, all of our energy is potential energy, right? So our total energy, what we often call mechanical energy, right? So at the end points, all of our energy is potential. So when you're at maximum position, there's no kinetic energy. So if you plug in your maximum position and find the potential energy there, that'll give you the total energy. Or at the midpoint, there's no potential energy, but your maximum velocity. So you can do this, right? This also shows you why the energy graphs are sine and cosine squared graphs because of the squareds here. Okay. So the idea then is, how do you connect the graphs? So the extreme values in your displacement graph correspond to points at which your velocity is 0, right? And your acceleration is also at its maximum, right? If you've got a maximum x, you're going to have a maximum force, which means maximum acceleration. All right. And notice your maximum velocity occurs at the middle, right? When you get back to that origin point, that's where your net force is 0. So at the origin, you're at your maximum velocity. And at the origin, your spring is no longer squished or stretched, so there's no force and thus no acceleration. Okay. All righty. Oh, I know what I wanted to do. So let's talk about the potential energy graphs. Or not just potential energy, but the energy graphs in general. All right, so let's do, I don't know, let's do U. Well, what order is it in on this page? Oh, I guess I didn't do it. All right, so let's do U as a function of t. Well, let's see. Let's kind of extend our dotted lines down. So let's see. So U is 1/2 kx squared. So here I'm at my maximum X. I'm also going to be at my U max, right? Oh, which I guess we can just call E, right? Right? Or maximum total energy. All right, so we're going to oscillate between that. Then when I get to here, my X is 0, which means my potential energy is going to be 0. Since X is squared, being here is the same potential energy as here. And then we're back down to X is 0, and then back to a maximum. So the energy, the potential energy graph looks like this. Whoop, 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 whoop. All right. And then our kinetic energy graph is going to kind of be the same thing, but inverted. Because now we care about the velocity. So let's look at our velocity graph. Oh, the velocity. Oh, here. Sorry, getting ahead of myself here. So let's see. Our velocity is 0. Kinetic energy is 0. Velocity is 0. Kinetic energy is 0. Velocity is 0. Kinetic energy is 0. And then here I'm at a maximum velocity. It's negative, but that doesn't matter. So because it's going to get squared. And same thing here. Oops. And so then we got to sort of make it look like a, I guess, a sine squared graph. So more, etc. There you go. So now that we've done that, let's run through a problem so you can see this all in action. All right, so we've got this graph. Position as a function of time. Notice I'm a jerk and I gave you the time in milliseconds and the position in centimeters. When I did this, I don't remember because I wrote out my notes last week because I'm stupid. I did end up converting everything. All right, so let's make a list of the kind of the stuff that we know. So given. What we know. First of all, we know that our X max is, according to the graph, it's 7 centimeters. So that's 0.07 meters. My period is the time it takes to complete one full cycle. Oh, that's TS. Oh, it tells us that's 40 milliseconds. So our period is 40 milliseconds or 0.04 regular seconds. All right. So that's what we know. And then A says to find the maximum kinetic energy of the block. So there's a bunch of ways you can do this. Probably the first thing we want to do is come up with an expression for this thing. All right. So first of all, I notice it starts at a maximum, which means that it's going to be a cosine graph. So I can do this. My position at time t is x max times the cosine of, oh shoot, omega t, right? So I got to figure out what omega is. Well, remember, omega is just 2 pi radians completed in capital T seconds. Oh, so that's 2 pi over 0.04, which gives you 50 pi radians per second, which means this is 50 pi times T, right? Omega times T. Oh, cool. Now I know my maximum kinetic energy. All right. So at this point, we could use the equations, right? I could go, oh, cool. Well, then K is m omega squared. Let's see. Do we know the mass? Oh, we do. I forgot to write that down when I wrote out the givens. The mass is 60 grams or 0.06 kilograms. All right. Well, you're just going to have to deal with that. So if you do 50 pi squared times 0.06, you get 150 pi. Do I believe that? 50 squared times 0.6. I'm nervous about that because I wrote these notes up last week. Let me check it real quick. So we're going to have clear, second, 50 squared times 0.6. Yeah. Ooh. Yeah. So you get 150 pi squared just by plugging in M and K. Cool. I guess I'm getting ahead of myself. All right, so now we know what K is. The question asks about the maximum kinetic energy. So where I was headed with this, here's one way of doing this. I can find my elastic potential energy max, right? Oops. Maximum by doing 1/2 K times X max squared, right? So here's my K value, here's my X max value, plug those in, and you get, I wrote down 3.6, but again, I'm nervous. So let's do this. 150 pi squared is my K divided by 2 times 0.07 squared. You know what would be awesome is if I knew how to use a calculator. 150, oh my goodness. I'm sorry, I'm a jerk. I should have had this ready. I'm wasting your time. Pi squared times 1/2 times 0.07 squared, 3.6, okay, cool. So that's 3.6 joules. So at the end points, we've got our maximum elastic potential energy. Oh, we should have that same amount of kinetic energy at our maximum speed, right? Because all of the elastic potential energy here becomes kinetic energy. So that's the answer to part A, 3.6 joules. What's another way we could have done that? Well, let's see. Some of this information I'm going to want. This will kind of help you guys sort of connect dots, as it were. What do all these numbers mean and how do they fit together? All right, so let's make a note. We knew what omega was, so we figured out. So K, we have since found out, is 150 pi squared. We know that omega is 50 pi radians per second. All right, so maybe a more direct way of solving this probably was your intuition when you read the problem. We're trying to find the maximum kinetic energy. KE is 1/2 mv squared. Oh, let's find the velocity. Oh, let's take a derivative. So my velocity at time t is the derivative of this. So derivative of cosine is negative sine of 50 pi times t. Oh, chain rule. I need to now multiply by the derivative of 50 pi t, which is just 50 pi. So I'm going to do 50 pi times 0.07, which gives 3.5 pi. Oh, cool. So that means that my maximum velocity is 3.5 pi, right? Because sine oscillates between 1 and -1. So the biggest velocity I could ever have is 3.5. So now I can find my maximum kinetic energy by doing 1/2 mv max squared. Plug in your maximum velocity, plug in your mass, and you get very satisfyingly 3.6 joules, which makes me happy. Hooray, physics. Cool. So that is that. Question B, the number of times per second the maximum is reached. I want to do this. Plus, let's switch to 2 pages. All right, so let's see. It looks to me like we reach our maximum. How do we want to do this? So our period is 0.04 seconds, and that's equivalent to hitting the maximum 1-2 times, right? Yes, and we don't need to count that one again. Why don't you count that one again? So if you imagine the period going from here to here, you can see that within that time you hit the max there and there. So every time you go through a period, you're going to hit the maximum 2 times. 2 maxes. And so then you would just set up a ratio. It says, what's the number of times the maximum? Oh, the number of times per second. So 1 second equals how many maxes, right? So just set up a ratio. 0.0, no, let's do 2 is to 0.04 as x is to 1 second, and then cross multiply. If I remember right, you get 50 times. All right, let's see. Part C, spring constant. We already found that, we rule. D, what is the velocity when it's at a position of 4 centimeters? All right, 2 ways to do this. you should understand them both. Okay. So option one. So this is part D. Option one. Trying to find the velocity when it's at a position of 4. So option one is find the time. So we know the position at time t is 0.07 cosine of 50 pi times t. So let's find the time at which the position is 0.04. So 0.04 equals 0.07 cosine of 50 pi times t. Divide both sides by 0.07. Now, I didn't write it all out. So let's see, on 4 divided by 7. So you get 0.571 equals the cosine of 50 pi times t. Take the inverse cosine of both sides to get, I should have my calculator in degrees, darn it. So times 2 pi divided by 180, which actually this is as good a time as any to say this. All of these rules that we're using for our derivatives, derivative of cosine is negative sine, all of that only works if your calculator is in radians. Plus these omega values are in radians per second. So we have to have our calculator in radians. So if you figure this out, you get 1.93 radians equals 50 pi times t. Divide both sides by 50 pi. And you get t equals 0.012 seconds, which is the same as 12 milliseconds. Same answer I had. Oh, we're not done yet. Oh, okay, cool. So that's the time at which that happens. So now what I can do is I can take that and plug it into my velocity equation, which I was trying to highlight and failed. Now I can plug my time back into the velocity equation, right? So this is the time at which I get to that position. So now I find the velocity. So now let's do that. I need to get to physical therapy. All right, so our velocity at 0.012 seconds is negative 3.5 pi times the sine of 50 pi times 0.012. So I'm going to take my previous answer and I'm going to multiply it by 50 pi. So that gives me the 1.92 radians again. I want the sine of that. And then times 3.5 pi, and it's negative. So you get, it's not the same answer I had before. All right, I'm sorry. I should have written these out before. So where are we at? So we were here. Because I had my calculator in degrees, it kind of messed things up. So this should have been 0.96, which makes the time 0.006. I'm super sorry, guys, which is 6 milliseconds, which then if you plug that into your velocity equation, then plug in the right time over here and solve for your velocity. And you get the answer that I originally had on my sheet, which is 9 meters a second. I'm super sorry for that little blip there. Cool. All right, so that's one way to do it. The other way to do it would be to use conservation of energy. And honestly, I think this way is easier in this problem. Because what I know is, remember, we already figured out our maximum kinetic energy was 3.6. That's our total energy. So total energy equals KE plus EPE, right? So our total energy is 3.6. Kinetic energy, that's 1/2 times the mass times V squared. That's what we're looking for, plus our elastic potential energy. Oh, well, we know that we're at a position of 4. So our X is 4. So this is 1/2 times K times x, which is 0.04 squared. And grind through your algebra and solve for your velocity, and you get 9 meters per second, which is what we got last time. All right, I think there's value in understanding both of those methods though. All right, cool. Sorry about the little mix up there. I think that's everything. Did we hit everything? I'm sorry, I've got my armpit in the camera. That is everything. Awesome. Have a good day.